Okay, now I'm back to the second part of the notes, and so what we said is we're going to do Bernoulli's principle, right? So there's actually two things: um, Bernoulli's principle and something that's not on the equation sheet that's called Torricelli's theorem. Okay, and so that is the last of the daily videos. It's called Torricelli's theorem, and so we have daily video 8.4.5 and a bunch of Italians here actually. Torricelli's theorem. And what Torricelli did is he made something, and it's actually not on the equation sheet, but he made a relationship, and we'll put a little star here, not on the equation sheet. He made a relationship that actually you're going to find out, oh man, I knew this. I knew this. I wish I would have done this myself. And so he takes a water tower. And so let's go back to the fact thing, and let's actually go to the right. It's water tower. And so this water tower, I can make the water tower lower, or I can make the water tower higher, right? What I want to do is I want to fill it with water, and I want to open it so water comes out, right? And water begins to shoot out, and the water goes that far, right? If I go lower with it, if I let the water drain out, do you see what happens to the distance it goes? Why does it go less distance? It goes less distance because there's less pressure, right? So pressure's involved there. There's a common way that people can show this. You take a bucket and you drill like 5 holes in the bucket, each 1 inch apart, right? And you fill it to the top, and water comes out, but water doesn't come out equally, right? The top one comes out kind of less, and the bottom one comes out kind of more, right? And so water's coming out of the bucket. Now I can keep this thing filled the whole time. If I keep it filled the whole time, I'm going to push here. I'm going to like have the water open, and it's going to fill up the whole time. And so all it's going to do, it's going to keep it at that same level. So how can I change how far it goes? Well, I can make it go lower. If I go lower, it's not going to go as far. Now the speed coming out will be the same, but it has less time, right? So this is my maximum time, right? But the really thing I want to look at is I want to stop filling it up. I'm going to go manual, and I'm going to do this, right? And as it leaks out, it leaks out, it leaks out, and it's going to get a shorter distance and a shorter distance and a shorter distance. Now, you got to notice one thing, is that this thing right here, it actually won't empty out if I don't have a hole in the top. It won't empty out if I don't have a hole in the top, and I'll talk more about that later. If there's no air getting in on the top, it won't empty out, and I'm going to tell you why that is in a moment. You actually have done this before. You've done this. You didn't know you did it, but you went to McDonald's and you had a straw and you figured out what I'm talking about. Maybe you know what I'm talking about already. Maybe you don't. But by the time we're done, you'll understand what I'm talking about. You know that time when you took your straw and you put your soda on your friend's French fries? No, you know what I'm talking about. Okay, maybe you're not as bad as me. Okay, so I've got this box, right? I've got this water tank, and this water tank is like this, and it's got a very small hole in the bottom like this. And I'm going to fill it with water, right? So I'm going to fill with water, and there's the water tank. It's filled with water, and but then I'm going to actually put it a little bit of a height above the ground like this, right? So here's the ground, and I'm going to brace it up like this, and we have to write small because Bernoulli's equation is actually a pretty large equation, but so then I'm going to say, okay, the height matters, right? So I need to be able to measure the height if I'm going to figure out what's going on here. And so what Torricelli said is he said, I can do the math and I can find out where this water is going to, how fast this water is going to go out. He didn't say I'm going to find out where it's going to land. He said, I'm going to do the math, and I know this water is going to shoot out right here at a certain speed. And I'm going to show you in my theorem what is this velocity going to be equal to? Okay, so that's really what Torricelli's theorem is. It's what is the velocity going to be equal to? Okay, so Torricelli said, you know what I want to do? I want to start off with Bernoulli. My buddy Bernoulli has an equation, and this is where we actually have to write a little bit small because Bernoulli has 6 factors in there, and there's a lot in there, so write small when we get to Bernoulli's equation. Bernoulli's equation is different than Bernoulli's Bernoulli's theory. Bernoulli's theory is basically saying that like a wing. So when you have a wing, when the air goes over the top of the wing, it goes faster because it has to go over this lump. And when the air goes on the bottom of the wing, there's no lump, and so the air goes slower. And so this has faster speed, and faster speed is lower pressure. And so since there's lower pressure above the wing, you get what's called lift. And so that's great, awesome, but that's not what we're talking about. We're talking about the Bernoulli's equation, and Bernoulli's equation is kind of a long equation. I'm going to leave a little bit of space on the top above this because I'm going to write something above it, okay? So we're going to write Bernoulli's equation, and Bernoulli's equation starts off with pressure. And so this is P1. Now, the important thing about this pressure P1 is this is an open system. It's not a closed pipe, and we'll talk about that more in a second. So P1 plus rho, that's a fancy P, rho GY, and this is rho GY1, right? Plus 1/2 rho V squared. And I wrote small because I got to write the same thing on the other side, right? So I wrote small. I probably should have squeezed it over a little farther even. I blew it. You have to write small. Okay, so on the other side, I have the same thing, but now I'm changing everything to 2's. So I have P2 plus rho G Y2 plus 1/2 rho V2 squared. This is V1 squared on this side. Okay, so he started with that. And then he said this, you know what? I'm going to try to see if I can derive for velocity. That's Torricelli's theorem. I'm going to derive for velocity. So a couple of things. First of all, he said this P is atmospheric pressure. This P here is atmospheric pressure. So I got some explaining to do here, because what he's going to do is he's going to say this is atmospheric pressure here, right there, and atmospheric pressure right here. And the thing about that is it's pretty much the same on both sides. They are pretty much top and bottom. They're pretty much equal. And so why can I get rid of that? Because they're the same. Now, what do you mean by they're equal? Are you kidding me? Well, I just said the air pressure was 100,000 pascals, right? 100,000, 10, 100 kilopascals. That's a lot of pressure. But you know what that's caused by? It's caused by 360 miles of air above our head. So how much difference in pressure is there between the top of this room and the bottom of the room if this was air pressure? The answer is 0, none, zilch, nada. It's pretty much nothing because there's 360 miles above your head, right? So there's not a lot of air pressure difference. Is there air pressure in this room? Yeah, a lot. But is there much difference between the top and the bottom? Now, you can actually feel this. Can you feel the difference in air pressure? Remember I said if you go upside down in a pool, you can feel the pressure on your ears? If you stand upside down, can you feel the pressure on your ears? No, you can feel the pressure of your blood on your ears on the inside because your blood is heavy. But now think about this. If I walk up a flight of stairs, do I feel a pressure difference in my ears? No. If I go down Thunder Hill, you sometimes can, if you're really paying attention. Why? Because I went down fast, right? If I go in an elevator really super fast, I can feel it. If I go on an airplane really fast, I can feel the pressure difference. But in order to feel air pressure difference, you have to have a pretty big distance between them. Does that make sense? So this is why I canceled those two pressures. Why are those pressures not water pressure? Because it's an open tank. What's on the left side or the upper side of this, above this layer of water? It's air. Why is there air above? Because I got a hole. Air can get in. Right? What's on the outside of this? Air. So the air pressure is actually pushing in here and it's pushing in there. But guess how much it's pushing? Equal on both sides. So that's why we got rid of it. So far, so good? Okay, next. What about the y's? Well, let's make the y's a logical position. You can choose y anywhere you want, but I want to find the speed right there. So I'm going to choose y here to be y1. That's my initial height, my initial y. And I'm going to choose y2 to be there. And that's smart because I only care about how fast it's going. Here, I don't care about it all the way to the ground. Right? So what is y2 going to be? y2 is going to be 0. y2 equals 0. Why is it 0? Because I chose it to be 0. That was my choice. It was a smart choice because now I can get rid of that. So far, so good? Okay, lastly, I want to get rid of one more thing. Isn't that awesome? I'm just getting rid of stuff. I want to get rid of this one. How can I get rid of this one? Are you telling me velocity 1 equals 0? And yeah, it does equal 0. It doesn't actually equal 0. It doesn't. It doesn't. But it does, right? The reason it doesn't, because if this is a giant volume of water, and this is a little hole, this is going to go out pretty fast. But how long is it take the tank to go down? A really, really long time. It takes a really long time. And so the velocity here is pretty much 0, right? It's not actually 0, right? This height is actually 0. This velocity isn't 0. It's just, I'm saying, like approaching 0. The bigger the tank, the more close that's to 0, right? Now, if it was a tube, let's say it was just a tube, just a tube, and it was a tube that was the same size here, and it went straight down, and it was the same size here, right? The speed would be the same everywhere in the tube, right? Because, you know what I'm saying? So this has got a big area at the top, and this has got a teeny tiny area at the bottom, right? And it's a circle. It's a big, giant circle, right? So it's pretty much 0. So what are we left with? That's a pretty easy, that's a pretty easy expression. It's just rho gy1 is equal to 1/2 rho v2 squared. And what is Torricelli's theorem? Torricelli's theorem is asking you solve for velocity. That's Torricelli's theorem. So can you solve for velocity here? Can you solve for velocity there? And when you do that, I hope that you find out, man, I should have known that. Man, I should have known that. Is it really going to turn out to be the same equation I had already done like 5 units ago? But it's an entirely different way. And that's the beauty of physics, actually. And if you're actually following me right now and not falling asleep, the fact that I'm going so fast on these notes, think back to when I had you in Unit 1 and we did the first MCQ. And you're like, there's no freaking way I'm going to be able to pass AP physics tests at all, right? There is no way that I could give you these notes this fast back in Unit 1. You've grown so much. Like some people, I didn't even tell you what this derivation is, but some people already know what the derivation is in the end, or go like, golly, I remember that derivation. So what does it turn out to be? Do you guys get it? What turn out to be? What happens to the rho here? It cancels out because it's the same on both sides. And what do you get as your final derivation for V? V equals root, and I'm going to, root, and it's actually 2G. I'm going to call it delta Y because technically speaking, that's what it is, delta Y, right? And if that doesn't make sense to you, then you're not remembering. That doesn't make sense to you, they're not remembering. That's pretty common that what we've had before. But we probably wrote it like this. V equals root 2GH. We might have wrote 2GY, I don't remember, but 2GH, something like that. And so this should look familiar to you. And so that's awesome because sometimes on a test, you guys will get the same answer as me. And then you're like, Mr. Morrison, I use different equations. How do I get the same answer? That's the point. In physics, like no matter how you do it, you're supposed to end up the same answer. And so the fact that we end up the same answer with an entirely different method actually proves physics. It actually proves that, oh, hey, we did a different way entirely, but we got to the same answer, which is actually kind of awesome, I think. Okay, so how fast is it going? Well, it's a relationship. V equals root 2G delta Y. Yeah, so far so good? So the notes themselves are kind of done. So what I'm going to do is I'm going to give you an example question. So example question is this. I've got a bucket, right? I've got this bucket, and it's sitting on the ground. And I'm going to fill it with water. And then I'm going to make a hole in the bucket, and it's not going to be exactly halfway. I don't want to make your life too easy. It's going to be kind of in the middle, but it's not be exactly halfway, right? And I'm going to call this H above the hole. And then I'm going to call this Y to the ground. Does that make sense? H is above the hole, and Y is the distance to the ground. That's a Y down there. I know I probably should have used a better pen or something that was a little more fine-tuned, right? So what's going to happen to this water, right? What's going to happen to this water as it comes out this hole? It's going to spray out, right? And then where's it going to land? Right? It's going to land there. And so what do we call that distance right there? We call that distance the letter x, and we call it range. And so derive the range, or derive x. Okay, so how do we do that? How do we do that? Well, let's go back. This is actually so much related to our last test. Not the last test, because we didn't do one in simple harmonic motion, but before that, before simple harmonic motion, we had these things. They went up the side of the cliff, went up the side of the table, and some of you guys blew it, and then you retook it, and you went, "Oh my gosh, I can't believe I didn't know that." The time is what? The time is the same for each one, right? And so we take the velocity times the time, and we're done. Why? How the heck can I take a simple expression like this and I say x is equal to what? It's very simple. X is equal to what? VT. Now, there is no equation on your equation sheet that says this. So you cannot get full credit for saying x equals VT, because it doesn't, right? Why can I say x equals VT? If you need to, look at the third equation down over there. X equals a red A, 1/2 times AT squared plus VIT plus XI, right? So in this case, why can I just simplify that equation to x equals VT? What's that? Because the a to the x is 0. Because the a in the x direction equals 0, and that way I can simplify that other equation and get this, right? This is absolutely positively what we did in the backside of the test, right? So this is review. So what is our velocity going to be? I'm going to derive this. What's our velocity going to be? Well, the velocity is going to be the velocity coming out here. Does anyone know what the velocity coming out here is going to be equal to? Oh, golly. What's it going to be? It's going to be root. I'm going to call it 2GH. And the reason I'm going to call it 2GH is I have an H there, right? Yeah. The velocity there is going to be root 2GH because I'm using an H on the top, right? Yeah. Okay. So then I say, okay, X equals V is root 2GH times T. You can do better than that. You're big boys and girls now. You can do better than that, right? What is happening right here? What is happening right there? It's a concept. What's happening as it travels through the air and falls to the ground. It's called free fall. And when an item is under free fall, what is the most important thing we need to know? That the a to the y equals, we're not going to say 9.8. And the reason we're not saying 9.8 is because we might not be on Earth. So if we're on Earth, we can say 9.8, be legit. We're going to call it G, right? And so the a to the y is down, and it's going to be equal to G. And then we're going to do a derivation. In the derivation, we can either do in our head, or we can just memorize it because we know it. Because we know it, right? So if we do the derivation, we use the same equation, right? And so the VI in that equation is gone because it's shot horizontally. What is the initial vertical velocity? 0. And so VI is gone. And so now I have x equals 1/2 AT squared. That's it. X equals 1/2 AT squared. And if I have x equals 1/2 AT squared, what's my derivation? So my time is going to be equal to 2 times y over g. Right? That's free fall. I plug that in there, and I have a nice, cute little equation. 2y over g. My physics brain really likes this equation. My physics brain says, "Oh, that's cool. This is my velocity as it leaves the thing, and this is my time that gets to the ground, and I know the range is x equals v times t, and that's the answer." My math brain, my physics brain always likes to win because physics makes sense, math doesn't. My math brain wants to call that a simplified expression. It does simplify a lot, actually. Right? What is root 2 times root 2? Root 2 times root 2 is 2. What is root g over root g? It's 1. What is root h times root y? Huh? HY, right? H and Y are not the same. And technically speaking, that's your math derivation. Your math teacher would like you. But that's not the physics derivation. My physics teacher wants to see it. That makes sense. Anyway, it works either way. And the notes are done. So now what you're going to do is you're going to take a look at the AP exam. And it didn't close. That's awesome. So if you look at not the AP exam, the last of our quizzes, the very last of our assigned quizzes. And so the very last of our assigned quizzes, you're going to see so many things that look so familiar. So you can go ahead and get your Chromebooks out and open it up. I'm going to show you up here, and let's track through this real quickly. It is the one that is Fluids Conservation Laws quiz, Fluids and Conservation Laws quiz. And if we go to that, you're going to see so many things look so familiar. So this is the first one. Does that look familiar? That should look familiar. That's actually a pretty easy question. Oh, there's actually something here I forgot. Now that reminds me, I got to go back to the notes real quick. Got to go back to the notes. So if we look here, how come I was able to cancel? And I need to add this to the notes just so you don't miss it. How come I was able to add these two, cancel these two pressures? It was atmospheric pressure, and the object was what? Open. It was open. So this is atmospheric pressure, and it is open to the air. That is so important. Open to air. And so let's think about this for a second. If it was not open to the air, would the water even have come out? And the answer is, technically speaking, no. You're thinking, like, really? Well, take your straw, put it in your soda, put your finger over the end of the soda, lift your straw, move it over to your neighbor's Big Mac, and drop it onto your friend's Big Mac. And like I said before, right? They say, why'd you do that? And you say, physics, right? Now, the neighbors are going to go like, I'm smart, and they put their straw, and they lift it up, and the fluid doesn't stay there. Put the straw and lift it up, and the fluid doesn't stay there. Why not? Finger has to be over the top, right? So as long as your finger's on the top, that fluid can't escape. Now, if I turn this upside down, you can't enter, right? If I turn it upside down, it's out. And that has to do basically with the shape of what's going on here. That water is going to kind of loop, and then air will get behind it, and then air gets behind it. You'll see air has to get in from the bottom, right? If I turn it upside down, it will leak out, but it will leak out in a kind of a little bit of a weird fashion, right? So air has to come out, air has to get in for it to leak out. If air doesn't get in, it will leak out, right? So that you can see the air, like the process going like that, right? So anyway, if you want to do something that's actually really pretty cool, take a bucket, go to your pool, submerge the bucket in the water, right? Like this, and you're like, oh, that's pretty buoyant, right? It's pretty buoyant, right? But like actually submerge it, turn it upside down, and try to lift it out of the water. It's actually really difficult to lift the bucket out of the water when it gets to that point right there. It's like that. It's like suction down, right? It's actually a pretty cool experience. If you haven't done it before, I wish you would just go in the pool and be a kid, right? Just do that. Try to pull out the water. It's a little bit different. So what's happening here is the reason I could get rid of those P's is because it is open to the air, right? And so that actually really has to do with this first question. As you read this first question, maybe you'll understand what I'm talking about. So we look at question number 2. Do these pictures look familiar? Right? Those pictures look familiar, hopefully. Number 3, does that look familiar? Remember, this is a top view, right? That's actually a hard question in some respects. It's an easy question in other respects. So what I would do is I try to answer this question, like give it a guess, and then do the rest of the questions and come back to it and actually solve it. And then we have question 4. Looks kind of familiar. Question 5 definitely should look familiar there. That should be an easy one, actually, by the way. Question 6, that actually is probably the question 3 and 6 are the 2 hardest questions on the test. This one is providing pressure, and it can show you where it's providing pressure. It's like a syringe, like you can squirt somebody with a syringe, right? That one's not the easiest one in the world. This one's actually pretty easy if you read this one. This one, that was not that. That's probably like the 3rd hardest question, number 8, and then number 9 is that. All right, so there you have it. You're going to work on these, and you did it. You done it. This is the last of the everything else from here on out until Friday is going to be review. So, any questions before we just close it off? You good? All right, get to the quiz, and let's see if we can answer the quiz questions.